Chemistry, Mrs. KJ here, going over 6.06 or 0.06 review moles. We're going to review concepts presented in the lessons mole mass relationships and mole mass volume relationships. In this lesson, you'll review those concepts, how they can be determined, and how they can be used to interconvert between numbers of atoms or molecules and mass or volume. Goals for the lesson: convert the mass of a molecular substance to moles, define molar mass, determine the molar mass of a compound given its formula and atomic masses of its atoms, explain what is meant by standard temperature and pressure, abbreviated STP, of a gas, define molar volume of a gas, discuss Avogadro's hypothesis, solve mole volume problems. And so you'll have to log into the lesson if you want to download the study guide. Key concepts in mole to mass relationships. So mole to mass relationships connects moles to molar masses. Molar mass is found using the formula, so the chemical formula, and the atomic masses, which are found where? On the periodic table. While 1 mole of any element, molecule, or formula unit contains exactly the same number of particles, so Avogadro's number, so it's the number, and this A down here stands for Avogadro, equals 6.022 times 10 to the 23rd. The mass of a mole varies with the substance. Just like if you had a dozen eggs and a dozen feathers, you have 12 feathers, you have 12 eggs, but obviously the eggs weigh a lot more. So just like mole, you have 6.022 times 10 to the 23rd of anything, but the mass is going to differ depending on what substance you're talking about. You need the periodic table and a chemical symbol to calculate an element's molar mass, or the mass in grams of 1 mole of an element or compound. So molar mass, the mass of 1 mole of a substance. For a compound, you can determine the molar mass by the sum of the average atomic masses of each atom in the chemical formula. So in other words, if you have carbon and oxygen, you need to take into account the carbon and the oxygen when you find the molar mass of carbon monoxide. Use these equations to interconvert between moles and mass. So mass in grams equals moles times grams per mole. Moles equals mass in grams divided by grams per mole. Some of you can do it this way and it makes a lot of sense to you. That's the minority. Most people, it works a lot better if we use the setup that I've been using in the other examples and when we do live CCs, because then you can easily see how everything's canceling out. Mole volume relationship derived from these equal measures. 1 mole of a gas is 22.4 liters, is also 6.022 times 10 to the 23rd gas molecules. However, for it to be 22.4 liters, the gas has to be at STP. It has to be at 1 atm for the pressure and 0 degrees Celsius, which of course is 32 degrees Fahrenheit. Key concepts in mole volume relationships. Gases are often reactants and products in chemical reactions. The volume of a gas is easily measured, but it changes with pressure and temperature. Think about a balloon. You can squeeze the balloon and the gas inside will take up less space. Think of a helium balloon in winter. If you take it outside, it shrinks down because the molecules lost some heat energy and they're moving slower. When you take it back inside, the helium balloon is back to its original size. What's the unit for volume? Volume is measured in liters. Chemists agree that standardized temperature and pressure, STP, is 0 degrees Celsius and 1 atm, which is the same as 100 kilopascals. Avogadro showed that at the same temperature and pressure, equal volumes of gases contain equal numbers of molecules, which makes sense since it's a mole, right? 1 mole at STP is 22.4 liters. Well, 1 mole is always 6.022 times 10 to the 23rd of something, in this case, the gas molecules. At STP, 1 mole of any gas occupies 22.4 liters. Use these equations to convert between moles and volumes of gas at STP. So I don't care if you use these, if this makes more sense to you, or if you set it up the other way. So volume in liters equals moles times 22.4 liters per mole. Moles equals volume in liters divided by 22.4 liters per mole. All right. So we have our mastery map. So go ahead and hit pause and figure out where everything needs to go. And you should be done before you see my answers, otherwise it doesn't do you any good. All right. And so now we're going to go to the problem book. Mole mass relationships. Objective, use the mole to solve molar mass and sample mass problems. You can use the mole to relate the mass of an individual atom or molecule to the mass of a sample of a substance made up of that atom or molecule. Chemists must often compare quantities of different substances. The same mass of different substances may contain very different numbers of atoms or molecules. For example, if I have 1 pound of feathers and 1 pound of eggs, am I going to have more feathers or more eggs? I'm going to have more feathers because it's going to take more of them to reach the pound. Therefore, it is more accurate to use the mole to compare macroscopic quantities, so big quantities of substances. We can calculate the molar mass of a substance, the mass of 1 mole of the substance, from the chemical formula and the average atomic masses of the elements in it. If we know a substance's molar mass, we can determine the number of moles of that substance in a given sample. Remember, the mole. The mass of 1 mole of a substance in grams is the same as the mass of 1 atom or molecule of the substance in atomic mass units. All right, what that means is, if we look at our periodic table, and let's look at titanium, okay? 1 mole of titanium weighs 47.867 grams. 1 atom of titanium has a mass of 47.867 AMUs. Okay, now remember we used AMUs. Let's look at lithium. 1 molar mass of lithium is 6.9 grams. So 1 mole of lithium weighs 6.9 grams. But 1 atom of lithium has a mass of 6.9 AMUs. And what did we use this for when we were talking about 1 atom? Well, we rounded it to a whole number. We said 7. So the mass of an atom is 7. 3 of those AMUs is because of the protons. 7 minus 3 equals 4. That tells us lithium also has 4 neutrons. So when we talk about 1 atom, we're talking about atomic mass units, and we're talking about protons, neutrons, electrons. When we do molar mass in grams, now it's the same number, but now it's how heavy 6.022 times 10 to the 23rd atoms of lithium would be, or how heavy a mole would be. 1 mole of a substance contains 6.02, I don't know why they put 23, 6.022 times 10 to the 23rd atoms or molecules of that substance. The molar mass of a substance is the mass of 1 mole of the substance. It is given in grams per mole, grams over moles. Calculate the molar mass of the compound. So we have C16H28N2O4, which is oseltamivir, a drug for the treatment of influenza or the flu infections. What's the molar mass? So see if you can hit pause and get it yourself. And so we need to take the mass of carbon, and the fact that there's 16 atoms, we have to multiply that by 16. So we have to account for all 16 atoms. So just the carbon is 192.18 AMUs. And in this, I don't like how they did it in AMUs. I would have just done it in grams. Hydrogen, there's 28. Each one weighs 1.01, so we get 28.221. For the mass of nitrogen, each nitrogen is 14.007, and there's 2 of them, so we have to multiply by 2. Oxygen, there's 4 atoms of oxygen. Each one is 15.999. Again, they should have rounded this to 16, so I'm not the happiest with how this workbook did. Your answer should have been close to 312. So if you're close to 312, you are good, because you would have rounded these all to hundredths first and then did the math. So you'll be off a little bit, but 312. In this model of the chemical structure of oseltamivir, carbon atoms are black, hydrogen are white, nitrogen atoms are blue, and oxygen atoms are red. So that's what it looks like. Calculate the number of moles in amyl acetate, which is CH3COOCH2 4CH3. This is organic chemistry, okay, where you have a lot of carbons and hydrogens. And it's used to make products smell like bananas. The molar mass of amyl acetate is 130.2 grams per mole. A chemist produced 183.5 grams of amyl acetate. How many moles of amyl acetate does the chemist produce? So just as a reminder, if the molar mass of a compound is not given to you, you can calculate it, but they gave you this one because this one kind of takes a while to count everything up. But again, that's like the last problem, so you should know how to do that. All right, hit pause, get your answer. So we start with what we know, what we're given. We're given 183.5 grams of amyl acetate. I would have put it over 1 just to make it look like a fraction. Grams of amyl acetate is going to be the unit on the bottom of my second fraction, so they cancel off, and we're converting it to moles. 1 mole of amyl acetate, because of its formula mass, because of its molar mass, is 130.2 grams. Put in your calculator, you should have got about 1.41 grams. All right, so you need to do problems 1, 2, and 3. So go ahead and hit the pause button and get your answers for 1, 2, and 3. All right, so we look on the periodic table to find the mass of our elements, and we look at the fact that there's 12 carbons, 22 hydrogens, and 11 oxygens. And again, your answer will be close to 342.29 because you probably rounded these all to hundredths like I tell you to in the class. Question 2. We are converting grams into moles. So we start out with grams of iron sulfide. Our unit on the bottom of the second fraction is grams per iron sulfide. 1 mole goes on the top because 1 mole of iron sulfide equals 87.92 grams of iron sulfide. Put it in your calculator. You should get about 0.64 moles of iron sulfide. And problem number 3. We're starting with moles, so that means moles goes on the bottom of your second fraction. 1 mole of sodium hydroxide is the same as 40 grams, and which is going to give you about 56.2. Okay, your answer is actually 60.8. I'm not sure what happened here, but this 56.2, it copied from up here, and that divided by 87.9, so ignore that. What you did was 1.52 times 40 is going to give you an answer of 60.8 grams. And if you're supposed to write it to hundredths, you would write 60.80 grams. So here's your correct answer. And my recording device is not letting me back up and just change my recording, so sorry about that little bit of confusion there with the 56.2. Problem set 48, mole volume relations. Objective, use Avogadro's hypothesis to solve molar volume problems. You can use Avogadro's hypothesis to relate the number of moles of a gas to the volume of that gas at standard temperature and pressure. Avogadro's hypothesis states that equal volumes of gases under equal conditions of temperature and pressure contain equal numbers of molecules. Because the volume of a gas varies with temperature and pressure, chemists generally specify the temperature and pressure conditions under which the volume of a gas is measured. Because if you do your research at a station in Antarctica, you're going to get very different results if you're dealing with gas than if you would on the tropical islands in Tahiti. If no temperature or pressure conditions are given in a problem or experimental setup, the problem or experiment is assumed to occur at standard temperature and pressure, STP. Chemists define standard temperature and pressure to be 0 degrees Celsius, which is 273 Kelvin, and also 32 degrees Fahrenheit, and 1 atm, which is 101.3 kilopascals. At STP, the volume of 1 mole of any gas is 22.4 liters. That's about the size of 11 2-liter bottles of pop. Therefore, if you know the number of moles of a gas in a sample at STP, you can predict the volume of a gas. So, nitrous oxide, N2O, also known as laughing gas, is a colorless, almost odorless gas used as a mild anesthetic. It is also used to improve engine performance in race cars. A particular container holds 4.55 liters of nitrous oxide at STP. How many moles of nitrous oxide does the container hold? So we will continue this in the next recording, so get your answer before you start the next recording.